This video will be an introduction into Chapter 3, which will cover the integral, starting with Section 3.1 about the definite integral. The objectives of this video will to cover the motivation of integration, the why of why we integrate. We'll talk about approximating area, using the Riemann sum. We'll define a definite integral, and then we'll look at real-life applications of the definite integral. So let's discuss the motivation behind integration. Suppose we know the rate of production of a factory, which would be bicycles per day, or the flow of water in a river that could be measured in gallons per minute, or traffic over a bridge that's measured as cars per minute, or even the spread of disease, which would be newly sick people per week. And we want to know the total accumulation in each of these scenarios. Since the curve represents the rate of change, the area bounded below the curve will represent the total accumulation over a given interval of time. How do we approximate the area if the rate is represented by a curve? It turns out to be more useful and easier to simply use rectangles. The more rectangles we use, the better our approximation is. Suppose we want to calculate the area between the graph of a positive function f and the x-axis on the interval from a to b. The Riemann sum method is to build several rectangles with bases on the interval from a to b and sides that reach up to the graph of f. Then the areas of the rectangles can be calculated and added together to get a number called a Riemann sum of f on the interval from a to b. The area of the region formed by the rectangles is an approximation of the area that we want. So suppose that the area that we want is this that's bounded below the red curve in blue. Our best guess would be to draw rectangles of equal width, which we'll eventually call delta x, along the curve, the height of which will be f of x because we're going up to the curve with each rectangle. Notice that some of these rectangles are an underestimation and some are an overestimation. A Riemann sum for a function f of x over an interval from a to b is a sum of areas of rectangles that approximates the area under the curve. Basically, it's just a notation. We want to start by dividing the interval into n subintervals. These n subintervals need to be equal. Each subinterval will be the base of one rectangle. We usually make all rectangles the same width and call it delta x. The height of each rectangle comes from the function evaluated at some point on its subinterval. Then the Riemann sum is the sum of all the areas of the rectangle. So the area of a rectangle is base times height, and that's what you have in each of these sums. In each of the terms of the sum is the height times the equal width. The uppercase Greek letter sigma, which is represented by this symbol, is used to stand for sum. Sigma notation is a way to completely represent a sum of many similar terms, such as Riemann sum. Using sigma notation, the Riemann sum can be written as the sum from I equals 1 to n of f of x sub I delta x. The I is a counter, like you might have seen in a programming class. So this would be the expanded form of the summation. So let's practice. We want to approximate the area under the curve y equals x squared from x equals 2 to x equals 4 using right endpoint approximation with 4 subdivisions. Let's start by drawing the piece of the graph that we want to approximate the area under. Okay, we're looking to find the area under the curve y equals x squared, bounded from x equals 2 to x equals 4. We're asked to use right endpoint approximation with 4 subdivisions. The 4 subdivisions is going to be identified as n. You'll need to know the equal width delta x that's created from each rectangle. So delta x is going to have the formula b minus a over n, where a and b are the endpoints of your interval. So in this case, a is 2 and b is 4. So we have 4 minus 2 over 4, or 1/2. You can write this as a decimal as well. So delta x, the width of each rectangle, needs to be 0.5, which means we can go down here and break up our interval into 2.5 and 3.5. So if we go to draw our rectangles, right-hand endpoints means you need to start at the right-hand endpoint, which is x equals 4. So we draw our rectangle up to the curve, and then we want to go over until we reach our next endpoint. So that's what it looks like visually to have right-hand endpoints, but what we're looking at mathematically in summation notation using our Riemann sum would be I equals 1 to 4, f of x sub I times delta x. Expanded, we're looking at delta x times f of x1 plus f of x2 plus f of x3 plus f of x4. Now, in the case of right-hand endpoints, because we're starting with x equals 1, we're actually going to start with 2.5 because your left-hand endpoint is always x sub 0. So our delta x is 0.5. F of 2.5 would be 2.5 squared. F of x2 is f of 3, which is 3 squared. F of x3 is 3.5 squared, and f of x4 is 4 squared. So remember our f function here is y equals x squared. Then you can plug this in your calculator and get your right-hand estimation. The area underneath x squared from x equals 2 to x equals 4 is approximately 21.75 units. And we'll say units squared since it represents an area. Let's look at another example. Water is flowing into a tub. The table shows the rate at which the water flows in gallons per minute. So we have a rate, and the tub is initially empty. We want to use the table to estimate how much water is in the tub after 5 minutes. So we're focusing on the interval from 0 to 5. The best way to approximate the total amount of water collected is going to be using a sum. So we have a rate. We can think of our rate as our curve, and the area underneath it is going to be the total water accumulated. So we want to find an average between the left-hand endpoint rule and the right-hand endpoint rule to make sure that we have the best approximation for the total water collected. So let's start by looking at the left-hand endpoints. It's important to note that our delta x is given already fixed in the table, and it's going to be 1 because it's increasing in 1-minute increments each time. Our left-hand endpoints are going to start at our x0, which is going to be 0. So we'll have our delta x. I'll call this our left-hand approximation. And then f of x0 plus f of x1 plus f of x2, f of x3, and we'll go to f of x4 to get our 5 rectangles. So 1, 2, 3, 4, 5, starting at the left hand. Then we just plug in the values from the table. So our delta x is 1, f of x0 is 0.5, plus 1, plus 1.2, 1.4, 0.7. And then we'll use our calculator. So the left-hand approximation is 5.8. We'll also do the right-hand approximation, and then we'll average the two. It's important to note that the units here will be gallons. So we'll still have the same delta x, but this time we'll start at f of x1 so that our sum ends at f of x5. Still 5 equally spaced rectangles, but we want to end at our last endpoint on the interval. So our best estimate for the total water accumulated in the tub is going to be the average of our left hand and right hand estimates. So 5.8 plus 7.3 divided by 2, 6.55 gallons. The definite integral of a function over an interval from a to b is the signed area between f, the x-axis, and the vertical lines x equals a and x equals b. If the function is positive, which means that it's above the x-axis, the signed area is positive. That's the area that's bounded between the curve and the x-axis as before, and we can call it area. If the function dips below the x-axis, the areas of the regions below the x-axis come in with a negative sign. That's because the function values are negative. Your f of x values are going to be negative, and it's going to try and resemble negative area, but we can't have negative area. So in this case, we cannot call it simply area. These negative areas take away from the definite integral. So this would be the integral from a to b of f of x dx is the area above the x-axis minus the area below the x-axis. That's our assigned area. If f of t represents a positive rate in y units per t units, that's going to be your rate function or your integrand, then the definite integral of f from a to b is the total y units that accumulate from t equals a to t equals b. If f of t represents any rate, then the definite integral of f from a to b is the net y units that accumulate between t equals a and t equals b. So using the graph of f shown in the given areas of the several regions, we want to evaluate each of the integrals. So if we look at the integral from 0 to 3 of f of x dx, which is part A, we're looking at the area that's bounded from 0 to 3 below the curve. So notice that from 0 to 3, the curve exists above the x-axis, so it's all positive. The area bounded between the curve and the x-axis is going to be positive, and so we would say this is positive 5. Alternatively, if we look at the area or the integral from 3 to 5 of f of x dx, we're looking at the area that's bounded between the x-axis and the curve that's now below the x-axis, and so this is going to be negative. So it's not necessarily area, but it would be negative 3. And then the integral from 5 to 7, the curve is above the x-axis, and so that will represent a positive area or 2. Now we can extend this, and we can consider the integral from 0 to 7 of f of x dx, which is our positive 5 minus 3 plus 2 for a net area of 4. We've already seen that area under a graph can represent quantities whose units are not the usual geometric units of square meters or square feet. For example, if t is a measure of time in seconds and f of t is a velocity, so again, our integrand has to represent a rate here, and the velocity has the units feet per second, then the definite integral is going to have the units of feet, and that's found by taking feet per second and multiplying it by seconds. In general, the units for the definite integral will always be y units times x units. So that's going to be the units of the integrand times the units of the independent variable. So let's take a look at an example. If the units for x is time in hours and the units for f of x is a flow rate in gallons per hour, we want to identify the units of the integral from a to b of f of x dx. So the integral from a to b of f of x dx will have the units, which will be the units of f of x, which are gallons per hour because it's a rate, times the units of x, which are hours, and we end up with gallons. So the integral from a to b of f of x dx, the result of that will be in gallons. In the next video, we'll talk about the fundamental theorem and anti-differentiation rules.